organizing this excellent workshop.
Oh.
And talking of the bottoms, here is essentially the bottom line of my previous part of part one. So I introduced the protocol, the precise quantum mechanical protocol of measuring the charge, and announced an effect. I didn't explain when the effect emerges, but I just described the effect in terms of the measuring of the charge. Here is an example. So in this example of my measuring protocol, the charge is the sharply defined quantity, it's 0. However, the outcome of my measurements comes in two distinctively different pictures. The left panel outcome 1 and the right panel outcome 2. And I must admit that Felix asked a very relevant question, allowing me to a little bit elaborate on the protocol, because in terms of just measuring the charge and doing annihilations, which I introduced previously, at some point of renormalization of the image, I was supposed to annihilate this red dot, meaning the negative charge, and this blue dot. However, in terms of emphasizing the essence of the Halon effect, in terms of the emphasizing of the quantum entanglement, I need to introduce yet another very simple feature. I must say that if at a certain point, at a certain distance, I see a well-isolated charge, in this case, it's -1 red dot, I have to protect it from further annihilation. All this piece, the measurement by Alice, because we are talking of the entanglement in precisely Alice-Bob setup. So in this case, Alice, which does her measurement at a short enough distance, but large compared to the typical interparticle distance, here Alice sees 0, here she sees -1. And now Bob performs his measurement at large distances, and here Bob sees 0 and here +1. So the net outcome is always 0, but this 0 comes in the form of quantum entanglement. 0, 0, 0 at short distance, 0 at any larger distance, or -1 at short distance and +1 at large distance. So a typical example of entanglement. By the way, in my example, I will show that actually the probabilities will be 50-50, like as if Alice and Bob are sharing a singlet. Okay, so I announced the Halon effect, but I didn't give you a single example of when do we see this effect. Here I can just mention one very simple example, very relevant to this workshop. It's a Fermi polaron, but not just a generic Fermi polaron, but a Fermi polaron with heavy mass. So a Fermi polaron with heavy mass, it's important that it's mobile, because for the static Fermi polaron, we do not have charge as well defined as a sharp quantum number. So for the heavy enough Fermi polaron, we would have precisely this effect. Time permits, I will discuss this setup in a little bit more detail at the end of my talk. But for the heavy Fermi polaron, we will have precisely this situation. The charge will be a sharply defined 0, unless it's a molecule, and it will be a sharply defined 1. And this sharply defined charge will be coming in, if you will, two pieces. The piece near the impurity, mobile but heavy impurity, and the piece away from the mobile impurity. And the sum is supposed to be equal to either 0 or 1, sharply defined quantity. And the distance between this blue dot will be controlled by the inverse mass of a heavy pole. However, the main part of my talk will be about different and far more sophisticated environment than the heavy Fermi polaron. So here is yet another slide which I was showing, which is closely related to the notion of quantized charge. Essentially, I'm saying that it's interesting to discuss the transitions between two sectors of quantized charge. And my point was that the majority of those transitions, when the charge is a well-defined quantity, are trivial. it's essentially either coexistence or asymptotic metastability, which is close to coexistence. And a non-trivial question, which I will answer positively, is that there exists a scenario of essentially critical endpoint when two sectors meet at fluctuational critical point. That's the main message I want to deliver. And my point is that the system in question, the system which demonstrates this weird behavior, is a static impurity in a quantum critical environment, specifically in a two-dimensional quantum critical environment corresponding to the superfluid two-mode insulator quantum phase transition. So here are collaborators on this part of the project: Kun Chen, Yuan Hong, and Eugene Deng. By the way, the term Halon was coined by Kun. Also, the theorem which I will be mentioning on the next slide, an important theorem, was also found by Kun. So for aesthetic impurity, actually, we need a really non-trivial regime for charge quantization to happen on one hand and to be non-trivial on the other hand. The environment is supposed to be incompressible, both incompressible, zero compressibility, and gapless. If the environment is gapped, the charge quantization is trivial and nothing interesting happens. It's just a coexistence transition between two charge sectors. On the other hand, if the environment is compressible and the impurity is static, this is important, then we have a theorem which I already mentioned, and the theorem is very simple. It says that for any compressible environment, the charge cannot be quantized if the impurity is static. If the impurity is mobile, it's a different story. The charge can be quantized. And the Fermi polygon is an example of quantized charge for a mobile impurity and in a compressible environment, which ideal Fermi liquid is. So the details of the theorem are also instructive. It just says that the charge of the medium created by an infinitesimally small local potential, mimicking the impurity, is proportional to the compressibility. Once the compressibility is finite, the charge is sensitive to an infinitesimal change of the potential.
I'm sorry, since we are talking about theorems, I'd like to understand the meaning of the words.
Yeah, sure.
Of the words here. So when you say about an operator, so a charge, I suppose, is a quantum observable. Your definition of charge is quite complicated, but it is still a quantum observable in the most classic sense. So, so it is a Hermitian operator. Okay, we all agree with that. So it is a Hermitian operator. When we say that the Hermitian operator is quantized, that means that...
Oh, no, operators are not quantized. Their eigenvalues are quantized.
Sure. Yeah, exactly. So when we say that charge of a particle is quantized, that usually means that...
I was giving a precise definition. Let me repeat it. The charge is quantized if quantum measurement retrieves one and the same quantum number. My measurement always retrieves integers. So if it's always 1, 1, 1, 1, it's a sharply defined quantized charge. If my measurement retrieves 1 or 2 with equal probabilities, my expectation value of the charge is 1.5. But the charge is not quantized because the outcome is probabilistic.
Right. So quantization is not understood as the spectral property of a Hermitian operator. It is a...
quantization, as always, the quantization is the property of the state rather than observable.
I see.
For any observable, the spectrum is defined by the observable.
Yes, indeed.
But the outcome of measuring this observable depends on the state.
I see. I got it. Yeah, thank you.
Okay, thank you very much. So my point is that even if the environment is incompressible but gapless, the Halon effect is not yet guaranteed. For example, the criticality which I already mentioned, the criticality of the transition from superfluid to mode insulator, does satisfy the condition that the environment is incompressible but gapless in 2D and 3D, not in 1D. In 1D, it's still compressible. However, it's only in 2 dimensions that we have this non-trivial Halon effect. In 3D, there is nothing particularly interesting. It's like coexistence. Also, think of a simpler example. Think of just a vacuum, thinking of the vacuum as if it's a trivial example of incompressible gapless environment. Obviously, it's incompressible because there is nothing to compress, but it's gapless because the energy of a particle at rest is 0. In vacuum, we do not have a Halon. Okay, so the setup is very simple, and apparently in this audience, I do not need to introduce it. It's all about ultra-cold atoms, bosons in an optical lattice. We have a commensurate filling, say filling factor 1. Any commensurate filling is good enough as long as we just deal with the quantum phase transition from a superfluid to mode insulator. So this criticality emulates O2 Wilson-Fisher conformal field theory. This is important. A bit later, I will explain why. Well, I can say it right away. We need an emergent particle Hall symmetry. It's important, emergency 2, in addition to kind of U1, which is being broken. And we introduce an impurity, which is a very simple potential bump. We just on a certain side of our lattice, we have a potential. So here is the Hamiltonian. We have hopping, square lattice, bosons hop. We have a critical value of the interaction in the units of hopping. So I said hopping equal to 1. And we play with this, with the strength of this bump, or well, doesn't really matter. And if we define the charge, equivalently define the charge as just the integral over the average density profile, that's how we can kind of observe our charge in our Monte Carlo simulations. So the simulations, so kind of, we have a theory which is based on first principle simulations by Röhm algorithm. This is a cartoon of what we do with the Röhm algorithm. So here is the bottom line of the scenario leading to the Halon. So there is a certain critical, so first of all, a priori, we do not know whether the charge is a good quantum number or not. The first statement is the charge is a good quantum number in this critical environment. So we do have a setup when we are talking of the phase transition between 2 well-defined sectors. So that's the first. The charge is a good quantum number in 2D. It's also a good quantum number in 3D, but in 3D, the transition is trivial. Here, the transition is non-trivial. And here is the scenario of this transition. So on the approach to the critical strength of the bump of the well, in this case, it's the bump. So the charge originally is 0, and then it becomes -1. So we do have a halo, we do have the Halon effect. So what the charge distribution does, it splits into 2 pieces. It becomes bimodal. There is a short piece, which on average is -1/2. Remember that kind of -1/2 comes probabilistically. Sometimes it's 0, sometimes it's -1 by our protocol. Alice sees, who sits next to the impurity, sees either 0 or -1 when measuring the charge, but on average it's -1/2. And then there is a halo, which carries the complementary charge of +1/2. And on the approach to the critical point, the radius of the halo diverges. That's the formula of the divergence. The divergence is critical. It's characterized by a certain critical exponent, nu, which we can numerically establish. And right at the critical point, we are left, if you will, with the fractional charge, -1/2 at the center, and the halo becomes the size of the system. And what happens when we go from the other side, the situation is similar, but the charge of the halo changes its sign from +1/2 to -1/2. So at this point, you're supposed to stop me and ask a sharp question. In your numeric simulations, how do you know that the charge is exactly -1/2? Because there's always kind of some error bar, numeric error bar. We do know that not only from our numeric calculations. What we know from our numeric calculations is the divergence of the size on one hand, and also we have a fundamental knowledge of emergent Z2 symmetry of our critical theory, right at the critical point. In our critical environment, is better to say, there is emergent particle Hall symmetry or equivalent to Z2 symmetry, meaning that whatever corresponds to the infrared physics, and when the halo diverges, its size is a part of the infrared physics, it should respect the emergent Z2, the emergent particle Hall symmetry. So whatever is true for particles should be true for holes. So meaning that if the charge +1/2 of the, or any charge of the halo takes place, the negative charge should also take place on the other side of the transition. But we do know that we change the total charge by exactly 1. And this immediately tells us that the charge of the halo, twice the charge of the halo, is supposed to be equal to either 1 or -1. That's how we know that the charge of the halo is exactly 1/2, meaning that the charge at the center, which Alice would be seeing on average, fluctuating from 0 to -1, is exactly -1/2.
Sorry, how do you know that you change the charge by exactly 1 as you cross the transition?
Particle Hall symmetry of the emergent particle Hall symmetry of the critical O2 environment. This is the known property of the O2 environment, which emerges, which describes the criticality of the superfluid to mod insulated transition.
Right, that I understand. Okay, as far as I understand, the particle Hall symmetry is responsible for the charge of the halon on one side being equal to minus the charge.
Exactly. Then just double this charge, but you have to switch from 0 to 1. That's the constraint because the charge is a well-defined quantity. So you call the charge of the halo Q. Twice Q equals 1 or -1.
Yes. But why 1? Why is it well-defined? That's because
because the charge is the sharp quantum number.
Sure, yeah.
It is 0 or 1 or -1. The charge is the sharp quantum number.
I got it. That's because, is that because it's a gap phase on both sides?
Oh, that's an excellent question. We cannot prove it by hand waving. We can only establish it numerically. Numerically, we do see that the charge is the sharp quantum number.
I see. Okay, right.
By doing this, excuse me, just wait a second. By just doing this interval.
I see. So this is a numerical result. You can't prove it.
The sharpness of the charge is the numerical result. Excellent. Yes, absolutely. The sharpness of the charge is the numerical result. And that's the divergence of the halo is also a numerical result.
Right.
Then the known fundamental result of the emergent particle Hall theory tells us that this charge of the halo is 1/2.
I see. And is that a two-dimensional result? I mean, the sharpness, is that two-dimensional property, or does it work for 3D?
The sharpness also takes place in 3D. Moreover, it's an analytic result I will be mentioning.
Okay. Yeah. Okay.
In 3D, you can actually prove it.
Okay.
Sajdiv and his student, I will be mentioning, prove it in 3D, because 3D is a critical dimension when you do have a well-controlled RG. So in 3D, you can prove that the charge is the sharp quantum number, but the transition is trivial. I will be mentioning that. Thanks for asking.
Right. Okay. Thank you.
So this actually, I will be mentioning it pretty soon. So this is a kind of path integral visualization of what happens. So it's a path of a particle or a hole which spends a decent time in the halo and pretty much the same time next to the impurity. So now we are talking of kind of what I was just mentioning. So due to the emergent particle-Hall symmetry, which is Z2 symmetry, it makes perfect sense to deal with an exact mapping of our problem onto the problem which is Z2 invariant from the very outset, Z2 invariant microscopically. And this is the problem of spin 1/2 in the O2 critical environment. So this idea of kind of this setup was suggested independently by Sajdev and his student Richard and by us in a paper. But for them, it was just the setup for analytic treatment. For us, it was the observation that it's a nice model to simulate numerically better than the original model of bosons, because now we know the critical point. By microscopic Z2 symmetry, we know that the critical point corresponds to the zero pseudomagnetic field. So if this term is zero, this is precisely the critical point by symmetry. So I already mentioned that. So essentially, Suber and his students, Richard, were studying this model, which can be, the study can be controllably done, the RG can be controllably done in 3D, which corresponds to the critical dimension of the quantum criticality of the environment. It's also the critical dimension for this particular problem. So there is a controlled treatment saying that the RG flow nullifies the coupling between the spin and the critical environment. So the spin becomes asymptotically free in terms of RG. So that's why the transition is trivial, as if the spin is decoupled from the environment. But it's well defined. And this is kind of the answer to the question which we discussed. So the charge is sharp, the projection of the spin is well defined, speaking the language of the spin, but the transition is trivial, as if we have just a magnetic field which nullifies flipping the spin. In 2D, the treatment is not exact, but turns out that it is very reasonable. So let me show you the results. So here is the comparison of critical exponents with which Seth Richard and Suber Sajdev calculated in 2D using the RG treatment. There are two critical exponents. One is just the radius of the one which controls the radius of the halon. In the magnetic language, it's just the sensitivity to the magnetic field. And another one, complementary one, is the sensitivity to magnetic field in the XY plane. So here is the sensitivity to the radius of the halo, exponent nu, and this is the sensitivity to the magnetic field in the XY plane. Both exponents can be calculated by RG approximately, and also by Monte Carlo. So we calculated both, and here is the comparison. The comparison is very favorable. So it turns out that RG, excuse me, is pretty accurate. Nice news. So I already mentioned, so I'm pretty close to the end of my talk, but I really want to mention the heavy mobile Fermi polaron. So I already mentioned this problem. So here I have two collaborators, Kuhn, whom I already mentioned, and Nikolai. So I must admit that this problem we didn't publish a paper yet because we really want to do some numeric simulations, but somehow we didn't have time to complete this part. But the bottom line at the level of dimensional estimates is very simple. So as I said, the key observation is that the charge is quantized for the mobile polaron, but is not quantized for the static one, meaning that when increasing the mass, we should split the cloud of fermions, the fermions of the Fermi sea surrounding our impurity, into two pieces, the short range one and a halo. In this case, it's not like splitting in two equal halves like in our critical problem, but some splitting should be there. And you can do easily estimates. So this is a reminder that actually for mobile resonant Fermi polaron, the charge is a sharp quantum number, which is really important, because without having charge, as a shock quantum number, there is nothing to discuss. So then when we go to the heavy polaron, we do basic dimensional estimates. We want to estimate the characteristic radius of the halo, and also we want to understand the sensitivity to the temperature, because you see this Halon effect for heavy fermi polaron is extremely fragile. The larger is the mass, the more fragile this effect with respect to the temperature. By the way, the same is for the Halon in the critical bosonic environment. The closer you are to the critical point, the larger is the size of the halo, the more sensitive you are to the temperature. So the temperature can actually wash out the halo. So the generic statement is if the halo is very large, it's very sensitive, very fragile with respect to the temperature, and temperature would just wash out the halo. And we need to do some estimates showing how important, how dangerous is the effect of temperature. And here are some basic estimates. So this is how the radius of the halo scales with the mass ratio. It's a very simple dimensional estimate. And this is the temperature, which essentially washes out the halo. So the smaller is the mass ratio, the smaller is the temperature in the units of Fermi energy, which washes the halo out. That's it. Thank you very much.
Okay, since Misha is not here, there's nobody to stop the recording, by the way. Anyway, any questions in the lecture hall?
So can you just specify the O2 symmetric model? Because you didn't write down the complete Hamiltonian.
If you can write the complete Hamiltonian of the O2 model, you will get a Nobel Prize, because it's the critical theory, right? So the critical theory, we do not have Hamiltonians. We just know the Hamiltonians leading to the critical theories, right? And the Hamiltonian leading to the critical theory is just the Hamiltonian describing bosons in an optical lattice.
Okay, but so then how do you map it onto the spin and the psi dagger?
Oh, good question. That's a good question. So if you are asking me, can we do some microscopic model along the along the lines of having a Z2 symmetric model which does this criticality, then the answer is yes. Thanks for asking, because there is a certain difference between Sajjev's paper and ours. So in Sajjev's paper, they really do the critical theory, critical RGN stuff. In our case, we actually precisely answer your question, how to write Z2 symmetric microscopic model featuring this property of Z2 symmetry. It's just essentially a quantum rotor model of generalization of the quantum rotor model. So it's a model in which the particle Hall symmetry is there at the microscopic level. So the answer is quantum rotor. A family of quantum rotor models feature microscopic Z2 symmetry.
Okay.
Are there any questions from you? Let's thank the speaker. Okay.
So can I ask another one?
Okay.
So for the heavy Fermi polaron, so again, there will be these two possible outcomes of the measurement.
Yeah.
The one with zero, nothing, and the one where you have the basically a hole, say near the impurity and the particle far away, right?
Yeah.
And so the probabilities of these two outcomes in the limit of very heavy impurity, one of them will go to zero, and the other, one of these probabilities will go to zero, right?
Excellent question. There is a very simple way to calculate those probabilities. What you need to do, you need to do a very simple problem of just static potential and ideal Fermi gas in a static potential. This will give you the distribution for the charge at the local distance. This is an easy problem to solve. This charge is not going to be quantized. You just put ideal fermions in a short-range potential, fermions at finite density, and see what is the bump of the well, depending on the size of the potential. This gives you the charge in the vicinity of your static impurity. And then you figure out the probabilities, because the probabilities are proportional to those fractions of the net charge zero.
Okay. Thanks.
What I didn't get from the talk, do you understand? So, right. So it seems that your message is that the charge of an impurity, if it is a mobile impurity, is a sharply quantized quantity, which sorry?
Sometimes, no. Sometimes it's a sharply quantized quantity if it's a particle in the Fermi sea.
Yes.
Sometimes it's not.
Yeah.
Suppose it's just a particle, a mobile particle in the bosonic environment.
Right.
Its charge is a bad quantum number.
Same
with superfluid quantum environment. If you put a mobile impurity into a superfluid quantum environment, when corresponding symmetry is broken. So breaking the symmetry, breaking U1 symmetry responsible for the conservation of charge.
Sure. Yeah.
Immediately leads
to the
situation when the charge is a bad quantum number.
Sure, that is not surprising. But yeah, but in a situation when there is no, let's generalize. Can you indicate, maybe, do you have a complete or a good understanding of the conditions when the mobile impurities charge is quantized as opposed to the case when it is not quantized? So do you have?
I'm afraid not.
No. Okay. So
I can suggest something that the impurity should be mobile on one hand, and the environment is not supposed to break U1 associated with the charge. My bet would be the following: the impurity should be mobile on one hand.
Yes.
And the environment should not break the U1 global U1 symmetry,
right? Yes,
of the medium. That
so those
charge would be a good quantum number.
Those would be the necessary conditions, rigorously speaking.
Yeah, but I suspect they would simultaneously be sufficient conditions.
Yeah, and so that's your conjecture. That's a conjectural statement. Which
that's a conjecture, absolutely.
I see. Very interesting. Okay, thank you.
On behalf of organizers, we're asking again the last Mohican who stayed all these talks, do you have any other questions? Okay, in such a case, I stop recording. Don't disappear.